to invite Dr. Jingchuan Zheng to give us a technical talk. At the very first beginning, I would like to briefly introduce Dr. Jingchuan for all of our audience. Dr. Jingchuan Zheng received a bachelor and master degrees in mechatronics engineering from Shanghai Jiaotong University, Shanghai, China, in 1999 and 2002, respectively, and a PhD degree in electrical and electronic engineering from Nanyang Technological University, Singapore, in 2006. In 2005, he joined the ARC Center of Excellence for Complex Dynamic Systems and Control, School of Electrical and Computer Engineering, the University of Newcastle in Australia, as an research academic. From 2011 to 2012, he was a staff engineer with the Western Digital Hard Disk Drive Research and Development Center, Singapore. Since 2012, he has been with the Swinburne University of Technology in Melbourne, in Australia. He is currently an associate professor with the Faculty of Science, Engineering and Technology at Swinburne. He is also the major discipline coordinator of robotics and mechatronics engineering and the theme leader of field robotics research in the Manufacturing Futures Research Institute. His research interest includes high precision motion control systems, electrical vehicle control technology, mobile robots, and biomechatronic devices. He has published over 120 papers in refereed international journal and conference proceedings. Dr. Zheng is a senior member of IEEE. Now, let's give a warm welcome to today's guest speaker, Dr. Jingchuan Zheng, to start the talk.
Thanks to Hai for your introduction. Okay, and thanks for the invitation to this seminar. So now I will share my screen. Okay, can you let me know if you could see the screen?
Yeah, we can see that. Thank you.
Okay, good. Okay. All right. Good afternoon, everyone. Okay, so it's my pleasure to take this opportunity to share and discuss one of my research area, that's design and advanced control of dual-stage actuator systems. So in this talk, I will firstly discuss what and why is dual-stage actuator control system. Okay, or that's the motivation of why we study this dual-stage actuator system. And I began this research actually around 10 years ago. Okay, since after my I graduated from PhD study, and I'm keep working in this area as well. And then I will go to the part one. I will focus on the linear dual-stage positioning control system. I will introduce the dual-stage configuration that we built in the lab, and there's some control problems of the dual-stage actuator systems. And then I will introduce one of our proposed nonlinear control design techniques for dual-stage actuator systems. And we will follow by some experimental result to verify what we have proposed. And in the part two, I will continue to discuss some other dual-stage mechatronic systems we have built or we have tested on the practical mechatronics dual-stage systems. So this include hard disk drive systems and also a rotary dual-stage position that we built from scratch. So the first topic is that why and what is dual-stage actuator control systems. So to begin with, I may start with the most common single-stage actuators. Actually, in the literature, you may not see single-stage actuator usually. You just see some linear motor or single-stage DC motor or those rod and pinion stage. This is the most common name that you will see. But actually, this is classified as single-stage actuators in this talk. So what I defined here is the single-stage actuator positioning device. It's basically its axial displacement is controlled by one single actuator only. So here, what I mean is that axial displacement, is only one axis, okay, rather than two axes, okay. So in the literature, you will see that there are multiple axis positioning systems, and they will be controlled by multiple actuators as well, okay. But here I'm talking about one axis, and it's controlled by one single actuator only, okay. So the reason for introducing single stage actuator is to easily to compare with what we propose here, dual stage actuators. Okay. So this one I believe you will be very familiar with linear motor systems. Okay. So this is the moving platform and is controlled by the a coil which is controlled by control current. And once we input the current to the coil here, and you will be through the magnetic force, and then you will move around this axis. Okay. And another one is the screw stage. So this is usually controlled by either a stepper motor or a DC motor, and through this screw transmission systems. So you will move this platform around this axis. And another typical stage is called rate and pinion stage. So you can see there's either a DC motor or stepper motor as well. And we use the pinion attached to the shaft of the motor, and then it will move through this rake in the linear positioning type. Okay, so in this type of motor or actuators, its main advantage is that it has a long range. Okay, usually it can be from a few centimeters to even half a meter or 1 meter. Okay, so ideally there's no problem for those kinds of actuators to extend its range to be large. Okay, and the other advantage is that it has a high load carrying capacity. Okay, usually it can carry from a few kilo to even 10 kilo of payload on top of it. Okay. However, there's some disadvantage that inherently within these actuators. So some of them is that a relatively slow response. Okay, so this means that the acceleration and also the speed cannot be increased significantly. Okay, so they have to remove a little bit slower. And the other one of the reasons for this is because of the moment of inertia, or we say the mass of the platform is usually large as well. And the other reason is that because of the nonlinearity, okay, inside those stage, for example, the friction, backlash, okay, kind of this nonlinearity also constraint is response speed. And another main disadvantage is the low precision. Okay, so similarly to the reason that I just mentioned, those nonlinearity also constrain greatly of the precision that it can achieve. Okay. So for single stage actuator, actually there's another kind of motor or actuators. So one of the example is the so-called voice coil actuators. Okay. This system usually consists of two parts. This one is the permanent magnetic, and then this is the coil. Okay, usually is wounded by the copper wires. Okay, and by input the voltage, and of course the current will go through this coil, and then you are controlled by this magnetic force, and then we can control this stage to move around this axis, and then by attach the slide and also the platform with this moving coil, then we can control this the displacement of this axis. Okay, and in this system you can see that there's a position encoder here for feedback control. Okay. Another bit class of high precision actuator is this so-called piezo threshold linear stage. So this is made by the company. This is one of the leading company that manufacture this kind of stage. It's called PI in Germany. This is the piezo actuators. Okay. The main feature of this kind of actuators is can provide nanoscale positioning accuracy. Okay, and in this kind of stage, we usually don't use the conventional transmission system such as the spring or this screw kind of things. Actually, we will use the threshold linkage. Okay, so that we can provide high repeatable and also high precision positioning. And also in recent years, there's a lot of MEMS micro actuators. They can provide very high accurate positioning performance. So this kind of actuators compared to these actuators is that it has a high precision and it can has a fast response speed, or equivalently it can have a high bandwidth in terms of the control perspective. However, the disadvantage of those kind of actuators is that it usually has a very short, limited travel range. Okay, so for example, in this kind of voice coarse actuator, usually it can only travel by a few centimeters. Okay, and not to say this one, for the piezo actuator, usually is in the order of a few hundred micrometers. And this MEMS is much less. Okay, so usually it's a few 10 to 100 micrometers range as well, and usually they have a very low capacity as well, a few 100 gram. Okay, and for the VCM usually it's a bit larger. Okay, up to kilogram. Okay, so these two kinds of actuator actually has their application area, and they are very popularly used in the industry and also in some research instruments. So let's look at these two application scenario. In this semiconductor wafer inspection, so this either it's a camera or microscopy. Okay, it's used to scan across the surface of this wafer. Okay, to detect the quality of this wafer. So here the performance that they requested is that we need to control this camera, this lens, to be fast and also accurate. Okay, so actually this will request the positioning system to have a higher resolution. Okay, so this means that we need to control this positioning device to be much more accurate, so that we can increase the resolution of this scanning of the surface. And the other application of this positioning device is in the 3D laser nano printing. Okay, so this figure comes from the Swinburne CTEM Center. So the 2 nano fabrication. Okay, so you can see that this is the material to be fabricated, and this is the laser. But you can see there's a scanning stage. It's used to move the sample or material in the X and Y direction. And in this area, it's required to fabricate a very specific pattern on top of this material. So in this case, you can see that there's something like a grid is required to make on this material, and the interval of these lines is required to be micrometer. And actually, to fabricate this 1 micrometer intervals, it usually will require the positioning system to have an accuracy to be sub-micrometer, even a few 10 nanometer. Okay. So the requirement in this area is that, okay, they are asking that if the positioning or the positioning stage could have a larger scanning range, so that they can put a bigger material on top of it, and then they can fabricate this material at one time. So at this stage, they're using the piezo scanning stage, but it's limited to be a few 100 micrometer range. So if they need to do a larger area of fabrication, they have to do this separately, and then they were using some other technology to stitch them. Okay, so definitely this reduces the efficiency and also takes a lot of more time to fabricate a part or a material surface. So here we can see that, okay, those applications, their performance will encounter bottleneck. Okay, when the technology and also the demand in those applications, in those discipline advanced. Okay, so the natural question will arise here: can we integrate 2 different types of actuator in one axis positioning control and attain the combined advantage from the actuators? Okay, so this is why I introduced 2 different types of motor and actuators in previous slides. And this is come to the motivation of our research. So the answer is, of course, yes. So the solution is that we can use the so-called dual-stage actuator systems. And in this kind of dual-stage actuators, we can combine the actuators in series. Okay, and the primary actuator, usually we call it coarse actuators. This is used to provide long range, although it has a poor accuracy and slow response. But we can accept this disadvantage they have. And then actually this will be compensated by the second actuators. So to compensate this disadvantage, so we need to have fine actuators so that it can provide high precision and fast response. And although it has micro range, but this micro range, again, it will be compensated by the primary actuators. So these two actuators, actually, they are complementary to each other. Okay, so we can have a combined advantage of long range, high precision, and high bandwidth actuation. So actually, this concept is used in the accurate high precision positioning system in recent years. But actually, the similar concept has been proposed for many years ago. For example, in the robotics manipulator. So in this robotic manipulator, they actually have another terminology. It's called macro and micro system. Okay, so mechanically they have similar concept, but again, they from the control perspective, actually they have a different meaning. Okay, this will introduce later in later slides. This is another example. Actually, this is what we developed initially to investigate the control method for dual stage. So in this dual stage setup, it has a linear motor as the primary actuators, and then we place a piezo positioning stage on top of it. Okay, and then we can see that they are placed in the same axis, so that they can be used to provide a position in this axis simultaneously. Okay. So so why dual stage actuator control systems? Here is some further comments. So the motivation that why we study this one is the improvement of the drive mechanism of a single stage system is usually at the cost of manufacturing period of the system or economical cost to fabricate the mechanics. One major question that the people will ask is that why don't you just improve the performance of a single stage actuators? Let's make it to be more accurate, or let's just make it to have larger travel range. Okay, of course this is also feasible, but the things that from the cost perspective, usually it takes more time and development period. Okay, and sometimes there are some technical challenges as well. So for example, for the piezo actuators, if you want to make it to have a larger travel range, you have to state multiple layers of piezo actuators in one single device. And usually it costs much more. And once it has a longer in the length, and usually it becomes more brittle to be break. Okay, so this is some technical challenge as well. So that's why we think dual stage actuator is a more cost-effective solution. Okay, because it only poses some control challenge. So mechanically, we just simply step two actuators in one axis, and then this is very easy to implement. The only challenge is that the control. So this is what I will introduce later. Okay, that's why we need to have some dedicated control algorithm for dual stage actuators. Okay. However, this is only at the cost of hardware realization, and the controller is implemented in an embedded microcontroller, so it's relatively cheap to implement it. And the dual stage actuator system actually has a large range of industry applications. So this includes machine tools. Okay, the macro micro robot manipulator can also integrate this dual stage actuators on top of it as well to improve the precision. The other one is semiconductor and also magnetic hard disk drive. So magnetic hard disk drive is one of the the application area that uses the dual stage actuator systems. So this will be in part 2 to be introduced. So let's look at the 2 examples here. The first one is called atomic force microscopy. Okay, so this is expensive instrumentations. Okay, to scan a sample profile. Okay, in 3D dimension. So you can see that in this bottom picture here. This is one sample. You can suppose this is something like a cell. Okay, we want to scan the profile of the cell. Okay, the 3D profile of the cell. And this is one of the commercial atomic force microscopy. Their working principle actually is not too difficult to understand. They use a cantilever. This is some prop. Okay, they use this one to touch the sample, and then you scan it in the 2D dimension by moving this prop. Through the piezo scanner. Okay, through the piezo scanner here. And then you can do the scanning of the samples, and then we have the laser sensor here to detect the height of this cantilever. Okay, sometimes we call it prop as well, and then you can know the height of the samples here. Okay, and because we can control the piezo in XY direction, so that we can record its XY coordination, so we can have the XYZ value for each point that the cantilever go through. Okay, so that we using this data, and then we do some data processing, then we can have this prop. Okay, so this gives the image of the sample profile. Okay, so as I mentioned again, the problem of this atomic force microscopy is that it can have a very high precision, but again, its scanning range is also very limited. If you want to scan a large sample of a large area of sample, okay, we have to do them separately and then do the stitch in the image through the imaging processing, and sometimes you bring some problem in the resolution or distortion of the image. So the research in this area is also how to integrate a secondary actuators so that it can improve the travel range, and last it's a scanning range. Okay. So another big area that dual stage actuator is applying, and actually is on commercial hard disk drive now, is the dual stage hard disk drive. So these photos comes from the Western Digital, which is one of the largest manufacturer of hard disk drive. In the old days, you can see that this is called a single stage actuators. Okay, so in this type of hard disk drive, we have to the servo engineer this to control this voice coarse motor, and then at the tip of this VCM, we call it VCM, is the magnetic read and write head. So we need to position this read and write head on top of the disk surface, so that we can read and write the data on top of this the track. Okay, the track is a circular track on this disk surface. Okay, so you can imagine that, okay, there are a lot of track, okay, condensed in this disk. Usually it's 2.5 inch. Okay, and desktop hard disk drive usually 3.5 inch. And this is a very typical form size of the hard disk drive. This form size is not changed, okay, over the last 10 years. Okay, but now the requirement is that we need to put more check, okay, more data checks on this service. Okay, so you can imagine that the check we are getting more and more much narrower. Okay, so this will require this positioning device here to be more accurate, so that it doesn't deviate from the check center when reading the data from the service. Okay, so in the old days, I say this is using a single stage VCM actuators here, and this can only achieve a 500 gigabyte data storage here. Okay, so this 500 gigabytes storage capacity can be translated to the number of the check, okay, along this service, and it can also translate it to the positioning accuracy of this voice coil motor actuators here. And because the requirement of the hard disk drive capacity is getting more and more, okay, so this will require you need to put more data track around this surface, and of course this is translated to be more accurate positioning device here. Okay, but the traditional single stage actuator cannot meet this requirement anymore. Okay, this is because of the hardware. We said that the mechanism constraints. Okay, so that's why a few years ago, those hard disk drive companies start to use a dual stage actuator positioning device in the hard disk drive. So you can see in this hard disk drive, they're using the piezo micro actuators. Okay, they put them in between these so-called suspensions. So this is suspensions is used to carry the magnetic head here, and then they have the primary actuators, the VCM. This is the traditional single-stage actuators. So by combining these two actuators, okay, through proper control algorithm, they can increase significantly the positioning accuracy. Okay, so that this will allow the nano trace center to put on this surface, and then you can put more data on there. So you can see from the data, this is a 4 times larger on compared to the single stage actuators, and this is compared based on the same form factor of the hard disk drive. Okay, so to explain this, actually, Western Digital, they have filmed a very short video to explain what is dual stage hard disk drive. So I feel that this is quite interesting and not quite clear to explain this concept. So let me just play this short video here. Oh, sorry. Okay. So let's keep going. Okay, so for the dual stage actuator system, this is my perspective. I just classified as 2 types. So if you classify the dual stage actuator system according to the motion type, of course it has linear motion and also the rotary motion. So in this talk, I will cover both of them. According to the fine actuators employed, usually it has used a micro actuator to provide some micrometers range as the fine actuators. And also there are some MEMS actuators that has been employed and also demonstrated. Usually they provide less travel range. It's just 1 micrometer or less, but it can provide a higher precision. Okay, so let me go to the part 1. This is the linear dual stage positioning control system. Okay, so this part is majorly come from one of the papers that we published a few years ago. Okay, so it's listed here. Okay, so this is our developed linear dual stage configuration. Okay, so actually this is nothing but just 2 commercial motors and actuators that we simply step them along 1 axis. So this is a linear motor, and this is the piezo micro actuators. Okay, and we didn't have any contribution on design of this mechanism here, because at that time our main focus is to investigate the dual stage control problems. And actually these 2 actuators are properly selected, okay, so that they can reflect some of the control problems that we will introduce soon. For the linear motors, it have 500 millimeter travel range, and it has a 1 micrometer resolution encoder, okay, integrate inside the linear motor. So you can see that this is the scale. This is the scale. It's used for position encoder to detect the positions. And it also comes with a power amplifier. So this power amplifier is basically a voltage to current amplifier. So we can use the controller to generate the control command, and then it will go through the power amplifier, and then it will convert it to current, and then generate the force to drive these motors. And the second actuator is the piezoelectric micro actuators made by PI. So for this stage, you can't see the piezo actuators because it's integrated inside the stage. And also there's a capacity position sensor, okay, integrated inside there to detect the its position. And particularly this position sensor is very accurate. It has a 0.2 nanometer resolution. And the travel range of this stage is the 30 micrometer totally. And in our control, because we need the bidirectional control, so we offset it to the middle of its range so that we can provide a bidirectional positioning control. And similarly, it comes with a piezoelectric amplifier. So this is basically a voltage amplifier. Its amplification ratio is 10. So the final maximum control voltage going to the piezo is the 100 volts. And for control implementation, okay, once we design a controller, we implement it by using the real-time disk-based system. Okay, so this is a high performance real-time and fast prototyping systems. Okay, so the problem of dual stage actuators. So if you look at this diagram here, so we have the linear motor, we have the piezo actuator, and this is the control input, okay, to the actuators and motor themselves. And this is the displacement of the linear motor, and this is the piezo actuator displacement. And because it's a dual stage, and they are placed on in series, so the final output of the dual stage will be Y, and Y will be just a summation of Y1 plus Y2. So you can look at, if you look at this model here, this is a dual input but single output system. Okay, so our control objective here is to make the total position output Y to accurately track a reference input. Okay, so this is the called seeking control problem. Okay, seeking control problem. Okay, and similarly, to make this seeking problem to be fast, we need to have a high bandwidth control loop. And another control problem of dual stage is accurate tracking response, or sometimes we can also call it good disturbance attenuation. So this is means that, okay, if you have some disturbance coming from the linear motor or piezo actuators, so by detecting this Y, then we need to have some control feedback so that we can regulate linear motor and also piezo actuators together to reduce this disturbance effect. Okay, so this is another main control problem. So in a hard disk drive, this is a very important control objective because this will determine the positioning accuracy and then determine how nano the track width could be placed on the disk surface, and then it determines the final hard disk drive capacity. But in our this research, we actually is focusing on the seeking response. So we are focused on to make this positioning stage to respond to a step reference as fast as possible. Okay, so this is why I highlighted here. So the control training in here is that, okay, there are two parts. The first part is that because this is not a square, okay, it's not a square multiple system. Actually, it's a redundant multiple variable systems. So let's say that, okay, if because there are two actuators here but only one output here, so if you have a desired output, but if you have the desired output here, and for the input, actually the solution of these two control input will not be unique. Okay, so this means that there are multiple combination of U1 and U2 can eventually give you a desired Y. Okay, so this means that you need to have a very proper coordination of these two actuators. Okay, so this is what we this is what we call here coordination control design for both actuators. Okay, so this is also related to how to allocate the control effort of the two actuators. So in this case, you need to carefully study the property also or the characteristics of these two actuators. So for example, for linear motor, okay, because its response is slow, so you can't expect it to respond very fast to a given reference input. But for the piezo actuators, we should design it to respond faster than a fast reference input. Okay, but for large reference input, we need to let the linear motor to respond it in priority to have a larger reference magnitude. Okay. So, and the second challenge here is because it's because the piezo actuators usually has a very limited travel range. So this is equivalent to the control problem is that there will have a actuator saturation problem. Okay. So actually, to be more specific, there you have a saturation block placed here. Okay. So this means that okay, you can't input randomly large control input U2 to the piezo actuators, because in practice it will cause the saturation of the piezo actuators. Okay, so these are two challenges, and also need to be carefully investigated when designing the dual stage actuators controllers. So regarding the seeking control, a very typical design method is that okay, the controllers for the two actuators are designed separately. So firstly, we let the primary actuators control loop to check the reference command, but it has very little overshoot. And then the secondary actuator control loop will follow the positioning error of the primary loop. Okay, so in this case, if you imagine that okay, the primary actuator can eventually check the reference input, and then the control loop is just follow the positioning error of the primary loop. So eventually, it can also achieve the desired YR. Okay, and the position, because the position error is compensated by the secondary actuator, so it can respond fast at the initial time. Okay. However, we observe that when the target tracker is beyond the secondary actuator's limit, these strategies are unable to minimize the total settling time. Okay, this is majorly because of the secondary actuator's limited range. Okay, let me show you in the next slide the diagram here, the figures here. So this is what I mentioned in the previous slide. So if you think that this is the linear motor response, given there's a step command goes in, for example, it's 100 micrometer. So the conventional method is that we design a linear motor to check this 100 micrometer, but there's no overshoot. Okay, when it approaches the target. Okay, this will result in the rise time is a bit slow because we don't want it to have overshoot, so we have to reduce the gain, the control gain. Okay, so it has to respond slower. This is also the character of the primary actuators, because it has a larger mass, it usually responds slower. Okay, and then the piezo actuators is used to respond to the same command as well, and then at the initial stage, it will respond very fast. Okay, but because it's limited range, so you will saturate. Okay, it can't go further. Okay, and then it will settle down to 0 again, because the primary actuator has reached the target. Okay, when at this range. And note that the total dual stage position output is Y1 plus Y2. Sorry. So eventually you will get this total dual stage output in this way. Okay. So to compare with our method, we actually design in the other way. We allow the linear motor to have some overshoot, here, and this will give you the benefit that it can respond faster at this stage. So it has a much faster rise time. So you see that compare with this result here, Okay, it reduced from 30 to around 10 in terms of the rise time. Okay, however, the linear motor has the overshoot, so this is not allowed in the most positioning system. But we can use the piezo actuators to compensate for this overshoot. Okay, so this is what the response of the piezo actuators. So we can see that in the rising phase is roughly the same as this conventional method, but to reduce this overshoot, we have controlled the piezo to go in the opposite way, so that this part is compensate for this overshoot. And again, this is the total dual stage output is Y1 plus Y2. And this, because it is a perfect compensation, so they will cancel each other. So eventually you get a total position output in this curve here. Okay. So compare this line with this line here, so we can easily see that the settling time is reduced from 20 to 10. Okay, to 10 millisecond. Okay, so this is our idea or strategy to allocate the control of the two actuators to achieve a much faster seeking response. Okay, so this is not difficult to understand, but actually technically or we say theoretically, it's not as straightforward to design such a controller. This needs some very careful and some sophisticated design method, okay, to achieve this perfect compensation of the overshoot here. Okay, and also linear control. We find that linear control cannot fulfill this goal, so we have to use some nonlinear control method. So this will be introduced later on. Okay, so this is what I mentioned in the previous slides. So this is we have to use nonlinear control to optimize the performance. And regarding the design steps, so we firstly will identify the dual stage system model. Okay, we use the state space, and then we need to identify the parameters of the dual stage actuator models. And because of the linear motor has significant friction nonlinearities, so we have to use some specific compensator to compensate this friction first, so that we can shift the primary actuator to be a linear model. This is to ease the control design of the dual stage control as well. And then we will propose nonlinear feedback control design for both the primary and then the secondary actuators. First part is the system model. So this is an illustration of the dual stage actuators. So we have this big M. This is to represent the linear motor stage. Okay, and then this is the control input. Then we have friction force. This cannot be simply ignored. Okay, in many cases this is simply ignored, but actually this is a significant effect on the steady state error and also the transient. Okay. There may have some disturbance applied on the linear motor as well. And this is the piezo actuators. So it's a model. It is modeled here as a spring and damper system. Okay. So this is the mass of the piezo actuator platform. So here Y is our control variables. Okay. So we want Y to follow a desired reference input. Okay. And here we have a few assumption. This is a very practical assumption. Okay, and we have a capital M. The mass of the linear motor should be much larger than this little m here. And we also have the travel range. The ratio of travel range is much less greater than 1. Okay, and similarly we have the control input amplitude larger than this ratio here. In our case, for example, this is M is a few kilogram. Okay, and for this little m of the piezo is just a few 10 gram. Okay, and not to say Y1 over Y2. Okay, this is a half a meter, but this is just in the order of micrometers. Okay, and the reason we make this assumption is that we want to simply ignore the coupling between these two actuators. Okay, so this means that okay, when this linear motor is moving, we can suppose that there is no interruption force going to this piezo loop. Okay, and similarly, if piezo is moving, it will not affect the positioning of the linear motor as well. Okay, by using these assumptions, this can be ideally just ignored. Okay, so this go back to the mechanism design that I mentioned earlier. You cannot just simply choose any motors or actuators you want and then simply combine them. Okay, this is where if you not properly choose them, then it will cause some control problems, or I'm not saying that it can't be solved. Okay, but it will give you some more difficulty in the control design. Okay. So this is the model dynamics. Okay, we use the second order model to model the linear motor and also the piezo actuators. So in this case, we use the linear model. Okay, we put the friction as a separate term in here. Okay, and the friction model, it has two parts. One is Coulomb friction, this is static friction, and this is a viscous friction. Okay, so the first part we will do a friction compensator to remove the friction effect. Okay, and this is done through this block diagram here. So this is very similar to the disturbance observer. Okay, the main feature here is that we use the inverse of the Planck model. Okay, so this GN is the nominal Planck model. So in our case, this can be just a simple double integrator. Okay, and the Q is a low pass filter. So we can design in this way. It's a three order low pass filter. The order that is chosen is because to compensate for the improper of the GN here. Because we do the inverse. Okay, so this will result in the improper transfer function. Okay, because if you think about we flip this one, so it will be s squared m times s squared. So this is not a proper transfer function. It can't be implemented in a controller. So we have to design a low pass filter to solve this problem. Okay, so this is a low pass filter, and we can just simply assume its dynamics is infinity fast. Okay, and of course you need to properly chosen the time constant, the top here, as high as possible. Okay, so through some calculations, then you can find that from U1 to Y1, okay, then you can get this transfer function. Okay, this is approximately to be a double integrator now. Okay, and this means that the friction nonlinearity is cancelled by this compensator. And this is the experimental result. So we do some experiment to verify that the friction is removed. So this is the original friction model, and after the compensator is implemented, we can see that okay, it's basically flat. Okay. So this is the model after the friction compensation. So we remove the friction, and now the dual stage actuator model is turned into a linear system, except this saturation here. Okay, we also explicitly consider the saturation in the control design. Okay, so the main design objective here is that okay, we firstly design a primary actuator because it's decoupled from the second actuators. Okay, so we can design the controller separately, and because our control objective here is the seeking control, so which means that we need to have a time optimal controller. Okay, to achieve the desired performance. So here we employ the so-called proximate time optimal servomechanism. This is a near time optimal controller. So near time optimal controller means that it's quite close to the time optimal bang controller. Okay, so the basic idea of PTOS is that we use a maximum acceleration at the beginning of the seeking stage. Okay, and in the halfway, then we'll start to decelerate by applying the maximum negative control input, and then when it's close to the target, then we switch it to a linear controller. Usually, it's a linear PD controller, so that we can have a smooth transition to the target, so that we don't have a control chattering. So this is the formula of the controller U1. Okay, it's designed in this way, and this is the linear region that I just mentioned. When it's beyond this linear region, then you will use a bump controller, and then when it goes to the linear region, you will switch to the linear PD controller. Okay, and this is how we design the gain of the controller here. Okay, so here that we recorded that we intentionally to design the linear motor to have some overshoot. So this problem, this desired feature actually can be achieved by designing this omega and also the damping ratio here. So what we need to do is that we just need to choose a small damping ratio, Z1, in the control gain, and then we can allow the linear motor to have some overshoot. Okay, so that we can achieve fast rise time. And this overshoot will then be compensated by the piezo actuators. So our main contribution actually comes to the control design for the piezo actuators. So through some analytic analysis, and also we do several rounds of research and test and calculation, we eventually find that, okay, U2 must be designed in this way. It contains a linear feedback control and also a nonlinear feed-forward control. Okay, so especially this H must be designed in this way. Okay, this is parameterized by the model parameter and also the control parameters from the primary actuators. Okay, and also we have F is parameterized by Q1 and Q2. Okay, and we have a nonlinear function gamma here as a function of reference input and also the total measured dual stage output here. And this function should be chosen to be varying from 0 to 1. Okay. So for the piezo actuator control design, and the linear control part is chosen so that the secondary control loop is global asymptotically stable and has a well-damped and high bandwidth dynamics. So this can be achieved by choosing the Q1 and Q2. And for feed-forward controller, so this is the main controller effort that is used to reduce the overshoot caused by the linear motor. Okay, so this is the most important part, and this can be done by the proposed H and also by choosing this gamma function. Okay. So some tuning guideline of the gamma is that it should be chosen as the function start from 0 and then gradually approach 1 as the check-in error converts to 0. Okay, because when this one converts to 0, it means that it has a well-damped piezo control loop, and then this control effort will be increased to reduce the overshoot by the primary actuators. Okay. So with this proposed controller, of course, we need to theoretically prove the overall system stability. So we have this lemma. So consider the dual stage actuator system that we formulated in the previous formula under the PTOS control rod, and also the secondary actuators under the proposed nonlinear control rod. And here we can allow any non-negative function gamma. You can choose any non-negative function gamma. Okay, there's no unit form of this gamma function, only if it's a non-negative function. Okay, and it's continuously in Y, then that we can prove that the overall control system will drive the total system output Y to check the step command of amplitude YR. Okay, so I will not give the proof in detail here. Please refer to the paper. But basically, our proof is based on the approved stability theory and based on the conversion input and bounded state property in the dual stage closed loop. And also from this lemma here, it's interesting to see that the value of gamma does not affect the stability, okay, of the overall dual stage, okay, system stability. So this allows us to properly choose this gamma function, and then it can improve the transient response. Okay, and this is the key property of our proposed control design. Okay, so to proceed, I would like to present some experimental results that we have done. So this is the modeling of linear motor. So we do the frequency response modeling. Okay, so we can see that it's quite match each other of the identifier and also the major one. But you can see that the linear motor has a low bandwidth, around 100 Hz only, because you can see that beyond this 100 Hz, we can see quite a lot of uncertainty and noise. Okay, here. So this represents some nonlinearity and also nonlinearity region here. Okay, so we can expect that this one has clean linear properties. This is the model of the piezo actuators. So it's related. It's quite relative clean. There's no noise and there's uncertainties here. And it has a bandwidth, the cutoff frequency around 250 Hz. Okay, and we can see that they are quite match each other, especially for below this 200 Hz. So for the experimental result, we firstly do the 15 micrometers travel range. Okay, so this is exactly at the range of the piezo actuators. So within this range, actually, we can't see any difference of the proposed control compared to the conventional control. And this is not surprising because we need to allow the linear motor to have some overshoot, and then we can use the piezo to compensate this overshoot. But within this range, we can see that the linear motor has a response quite fast as well. Okay, at the initial stage, so we can't expect the piezo actuator to improve further. Okay. So, but beyond the piezo travel range, we can see that there's significant improvement now. Okay, from 16 to 11 millisecond. Okay, and we can see that this is the overshoot reduced by piezo. Goes to 500 micrometer, so we can see similarly there's a 5 millisecond reduction as well. Okay, but we have to say that if this goes to much larger range, so because of the ratio of the reduction time compared to the overall travel time, it may be less obvious improved. So lastly, we do the disturbance restriction. We put some force disturbance on the linear motor. Okay, this is the disturbance. It's a multiple frequency disturbance. So first we switch off the piezo actuator. So this will represent a single stage linear motor system. So its positioning accuracy is within the around 8 micrometer. But once the piezo actuator is switched on, then we can see that it's basically reduced to the best accuracy. That's 1 micrometer. Okay, so this gives a very clear demonstrations of how the dual stage actuators to improve the tracking accuracy as well. Okay, sorry, how many time do I have?
The workshop will be from 5 p.m. to 6:30. I think
Okay,
for part two, you only need to give some brief introduction, and for your research idea, I think it should be fine. Yeah.
Okay, I will use 10 minutes to finish.
No worries. Thank you.
We discussed. Yeah.
No problem.
So the second part is the dual stage hard disk drive. So for these two, we basically don't propose some new control method. We basically use the proposed nonlinear control method, but we verified on top of this on these new systems. And for the rotary dual stage positioner, we involve some mechanism design from scratch, and we manufacture the positioner, and then we use the proposed nonlinear controller on it as well. So this is the hard disk drive we built in the lab. Okay, so it's not really a hard disk drive because the top cover is removed, and actually once it's removed, we can't use it anymore. Okay, but this is used in the lab. We test the control algorithm. So we have two piezo strip, okay, between the suspension and also the VCM actuators. And then for this piezo strip, it's very small stroke limit. It has only 0.5 micrometers. Okay, but usually this 0.5 micrometer. It has been much larger than the track width. Okay, it's a few hundred track width. Okay, so it's enough to do the regulation of the tracking accuracy. A main difference of the dual stage hard disk drive model compared to the one that I presented earlier, the linear motor, is that is more challenging to be controlled because there's a lot of high frequency resonant mode, and this is coming from the mechanism of the lightweight and also the thin mechanism of the VCM and also the suspension. Okay, so this actually, when implemented, all these resonance modes will cause the vibrations. Okay, and then you will significantly reduce the tracking accuracy. So we have to deal with this resonance mode by using some filtering techniques. So in our case, we use the notch filter, okay, to filter to damn this resonance mode. Okay, this is implemented in the VCM and also in the piezo actuator as well. And similarly, we will demonstrate the nonlinear control for the seeking response. Okay. So this is our block diagram of the control. So we have two main parts different from previous one. So we have the filter designed for the dual stage prompt, and then we have a state estimators using the measured output and also the control input to measure the state. And then we use the nonlinear controller, okay, to do the same thing for the tracking control. Okay, so this is the filter equation. Okay, so it's a second order, but it's multiple filter used to damage each resonance mode. So controller is similar to previous one. Okay, and then I just go to the experimental result. So we do the 0.5 micrometer tracking. Okay, so in this case, we don't see any much difference. Okay, even we have the overshoot by the VCM actuators. Okay, but they have quite similar. The reason for this is that the tracking length is too small. It's too small. So the piezo actuator quickly responds to this reference command, and it already reached the target already. Okay, so in this case, there's no much sense to use the proposed control method. But in the mid or large travel seeking range, it makes sense to use the proposed method. Okay, so you can see that for 2 micrometer, we have reduced from 38 to 0.38 to 0.3. Okay, and similarly for 5 micrometer, we have an improvement as well. So this is a summary of the overall. So maximally, if this is 3 second length, then we can have a 25% improvement. Okay, so for this range of the second, okay, it's important to have a hard disk drive, because when you do the data searching in the hard disk drive service, usually you will very often to control the magnetic read and write head around this range from 3 micrometer to 10 micrometers. So similarly, we do so-called track following. Is actually try to maintain the positioning head over a data check as accurate as possible. Okay, so we can see that this spectrum of the positioning error. Okay, so we can see that it will reduce a lot of frequency in the positioning error. Okay, and the PS3 sigma is reduced by 40%. Okay. So lastly, this is what we designed for so-called rotary dual stage positioner. So this is motivated by the hard disk drive form, but the hard disk drive is too thin and too small for some applications, especially for its very low capacity. And we are motivated by some application, for example, the surface inspection and microscopy. So this has come up to this design. So we will use the primary stage. This is a VCM actuators, and we have the piezo actuators, and we design this flexible pin, and then we have these 2 actuators to control the platform. So we can imagine the sample can be placed here, and then we can control the position. Of course, it's an arc position in this case, so this is why we call it rotary. Okay, and eventually we can achieve the performance here. We can have a 33 travel range in this arc, and then we can achieve a 0.15 micrometer accuracy. Of course, this accuracy is much smaller than hard disk drive, but think about the mass and also the overall travel range, and also the low capacity is much larger than the hard disk drive. So this is also reasonable. So the design we use here in the mechanism, we have to use the finite element analysis to do the mechanism design. So we ensure it has a low resonance mode and it has the desired displacement achievable by the piezo actuators. Okay. And this is the actuators we have chosen, some spec. Okay. This is the VCM. This is the so-called limited angle VCM. Okay. We can control the rotation angle of this one, but it's limited by 60 degrees only. And this is the piezo actuator that we use to insert into this slot. So by control the voltage of the piezo, then it can expand this pin, and through this pressure hinge, then it will push this platform to move in both directions. Okay. So in design this pressure pin, there's a lot of concern. We need to think about the shape, the dimension, and we need to think about what type of material to fabricate this one. Here we use the aluminum, this type of model, this type of aluminum. And we need to carefully design the hinge size, this one. And of course, we need to design the suspension properly as well. This suspension is working as a simple level motion amplifier. So think about it, it's only a few micrometer range here, but if you have a long suspension, then you will amplify. Okay, they will amplify the position at this topic, at this tip here. But there's some trade-off we need to carefully taken into consideration during the design. So if you want a large performance displacement here, you need to have a long suspension as well. However, this will reduce the resonance mode. Okay, so this means that it tends to easily vibrate. Okay, when you put a control input to the piezo. And similarly, for the hinge size, if you want a large displacement of the platform here, so you need to have a small hinge size. Small hinge size means that the thickness of this hinge size should be small, so that it's something like it's softer. Okay, so it is easy to push this one, and then it's easy to move this one with larger range. However, again, it will reduce the resonance mode as well, and vice versa. Okay, if you have a large hinge size here, okay, it comes with a higher resonance frequency, but it gives you a much smaller displacement here, so this is not desired. Okay, so this is some of the main concern here. So to reduce the combination number of the design parameters, we firstly constrain the length of the suspension versus the piezo displacement by 3. Okay, and then we use the finite element analysis to do some simulation. And basically, this is some iterative design process. Okay, until we find the final performance that we want. So we have to use some software, the case software, for example, the SolidWorks or Provi, to do some simulation of the mechanism design. So this is the hinge size with respect to the displacement achieved, and also with the resonance mode, and also with the maximum principal stress. Of course, you can't design a hinge size to be too thin, otherwise it's easy to be broken. Okay, so if you go beyond its principal stress of the material, then it will break. Okay, so eventually we choose the hinge size of 2 millimeters. So this is to give us a field 160 resonance frequency, and it will give us around 35 micrometer displacement. And for the stress, it's quite well below the maximum one. Okay. So this is a figure to show the model shape. Okay, how it vibrate, how it deform when the control input is at this first resonance mode. So in our design, we try to push this first resonance mode to be as high as possible. Okay. So this is the system identification. So again, we use the frequency response to do the modeling. Okay, and then eventually we use this measure model so we can derive a mathematical model. Okay, with the model parameters here. And again, we use the nonlinear control method to do the experiment. So this is a 5 micrometer. Okay, and this is the proposed one. We use the overshoot. Okay, so it's quite similar performance here. Okay, regarding the I didn't show conventional design here. I just directly show the proposed one here. Okay, so for this one we have the overshoot, and it's compensated by the piezo as well. So we reach this the second time. This is the 10 micrometer. Okay, so we can see that. Okay, it's quite smooth, settle down, and with a smaller second time as well. So lastly is the steady state position error. Okay, we just made the platform to be stay as the at its position, and of course we control the two actuators simultaneously, and there may have some uncertainty and disturbance or noise going to the control loop, and then by observing the maximum peak-to-peak value, okay, we can get a conclusion that it can maintain a positioning accuracy by the 0.05 micrometer. Okay, so in this case we use a laser Doppler vibrometer, or it's called LODV, as the measurement of the position output. Okay, so that's why we can reach this high positioning accuracy. But because of the sensor, this LODV sensor is very expensive. It's not practically to be used in all the dual stage system. If we use a lower resolution sensor, so we should expect that this positioning accuracy will be reduced. But in any way, the dual stage performance will be better than the single stage actuators. So that's our key points here to propose dual stage actuators. So this is a disturbance rejection as well. Okay, this is a piezo on, and this is a piezo off, and this is the sensitivity function to confirm that the dual stage actuator has a higher disturbance rejection compared to the single stage across this wide frequency range. So last slide, I want to show that we also build some other dual stage actuators here. Actually, we have used this one and supplied to some partners, research partners, for education and also the research. So this is a simple dual stage controlled by two DC motors. So this is a relative trip dual stage actuators, and we don't have very high control accuracy because we use the low resolution motors here, and also we have a trip position encoder here. And for this one has is a higher resolution. It's controlled by the VCM, and also is controlled by the piezo actuators. And this is the platform. Okay, this is the platform to be controlled. Okay, thank you. That's all for my talk. Any questions or discussions is welcome.
Okay, so thank you very much for Jing Chuan's fantastic, talk. And during this talk, we have, seen many fruitful outcomes from his research, particularly for the dual stage actuators. And by using the advanced, servo controllers, we have already seen that, the dual stage actuators have already provided, a larger travel range, higher position accuracy, stronger robustness, as well as faster response. So I believe this should be, a lot, beneficial for both researchers and engineers. So for all of the audience, do you have any question? Please feel free to ask. Thank you.
Hello.
Yep.
Okay.
Yep.
Okay. Hello. Firstly, thank you for your wonderful speech, and it's a really but I have a question. In slide 28, I didn't know what the function F. I don't know. How does it mean?
So for the gamma function, right?
Yeah, the function of h. I don't know the
function of h, right? Function of h.
Yeah.
So the function of h is given at the bottom here. So I have to say that, okay, in here we actually I can't easily say that how we get this one, but we do a lot of try. Okay, our main purpose here is to use this hedge to reduce the overshoot of the primary actuators. Okay, and we do a lot of calculations and finally get this analytic solution here.
Okay, I think it seems like again. I mean,
this is again, yeah, this is again. So if you say that you put a hedge here, and this element will times the area of the primary actuator, and this element will times the velocity of the primary actuators. Okay, in A1, so some of the parameters is coming from the model. Okay, only this F1, K1 is coming from the controller, the primary controller, and F2, K2 is from give me a second. F1, F2 is coming from the feedback controller of the secondary actuators, and K2 is from the primary actuators as well. So this means that to reduce the overshoot of primary actuators, this hedge should be designed to be relevant to the closely relevant to the primary actuator control loop.
Okay. But my question is this again? I mean,
this is again. Yeah.
Okay.
You can imagine. You can think this one is again. It's a control gain as well.
Okay. So is it derived from your experiments or from mechanical? No. From your design. Controller design.
Yeah, this is from my control design. This is our original contribution in derive this controller. It's a control gain. Yeah, you can think of it as a control gain, and this control gain is relevant to the model parameters. It's relevant to the controller gain as well, the other control gain.
Okay, so is it derived from the Lyapunov function or is it derived from experiments?
I would say that initially we derive this based on some simulation and also we do some calculation as well. But in the ultra verification of this gain is that you must satisfy stability stability requirement, right? And also apart from that, we need to satisfy this gain is designed to be able to reduce the overshoot of the primary actuators.
Yeah. So which one is more important? I mean,
in our case, both is important. Of course, stability is in the first priority. If the system is not stable, so not to say its performance, isn't it?
Okay. Thank you. And I have another question. It's I think which one do you think is more important, the mechanical design or the controller design? I mean,
this depends.
Yeah.
Okay. This is an interesting question, but it's a big question. Okay. I'll say that if you are doing the mechatronics, both are important. Okay. Because if you look at some literature, you can see that there are some so-called integrate mechanical and servo design, right?
Yeah.
What happened here is that if you have a very good mechanism, in terms of it has a very good linearity, it has a large control input, it allows a larger control input, it has no noise, it has no measurement noise as well. This will give you a very easy features in designing the controller. Okay.
Yeah.
And then in the other way, if you have a very bad mechanism, in terms of nonlinearity, lots of things, but if you have a very good control design method, a robust control method or optimal control method, that ideally could deal with all these nonlinearities, then that disadvantage of mechanism is not a problem. Okay.
Yes.
So this depends on which standpoint you are. If you are server controller, you are server engineer, and you don't do the mechanism. Okay, so what brings you is just a mechanism that is there. You can't do any change over there. Then of course control is very important. You need to focus on the control design.
Yeah. Yes. Right. Thank you for your answers.
No worries.
Thank you. Thank you.
In the industry, okay, for example, in the hard disk drive industry, they have both department. One is mechanism, the other one is the server department. But actually, they don't just work individually, okay, or independently. They have to work together to improve both. Okay.
Yes,
Yes,
right.
yes. Yeah, that's exactly because we are not from the mechanical or background, so we more focus on the control part. But in the industry, definitely they will be working together to improve the performance of control system. Definitely, yeah. Any more questions from our audience and guests?
I have a question.
Yep.
Sure.
Could you hear me?
Yeah, definitely. Yeah.
The volume is a bit low. Can you be
Speak
closer
loudly.
to the microphone?
Hello, Dr. Jin. I think your presentation is very insightful and instructive, but I have a question about the research direction or research area, because we know with the development of artificial intelligence, currently more and more control investigators are using more cutting-edge techniques such as the neural networks and deep learning or Markov jump systems, something like this. And with the development of mechatronic systems, the system will become more and more complicated. Sometimes it will be difficult for you to give the dynamic model directly. So sometimes people will use the techniques like the neural networks to simulate the dynamic model. So have you thought about this research direction, or how to combine the most cutting edge techniques with the traditional control? That's my question.
Yep. So those advanced learning, okay, neural network and also some so-called extreme learning definitely is a hot topic, and it will have a lot of potential application in the future. But regarding the mechatronics, especially for the area I'm working on, is the positioning system. What happened here is that okay, the object that we are dealing with is some mechanism. And this mechanism actually initially is designed to be quite linear. Okay, it's a linear system or it's a linear model. Its dominant working range doesn't involve a lot of nonlinearity. Okay, and because the reason for this is that we want very high precision positioning performance. So this is also required a mechanism to be quite linear. And in terms of this, is that if you have a very simple and linear model, okay, to be controlled, actually, in my perspective, it's a bit overkill by using some advanced learning method. It doesn't give very significant performance improvement. Okay, so unless you are dealing with multiple scale systems that involve multiple machine, that involve a lot of coordination, or that involve a lot of interaction among those machines, or you have a lot of nonlinearity in these systems, then I think that those advanced learning method or neural network will play a key role in doing the system identification and also doing some more intelligent control schemes. But regarding the very simple single input and single output system, especially is the linear systems, I don't think it will give a very significant performance improvement. Okay.
Okay, thank you.
Any more questions? I have one question from the conversation board. There's one guest raising one question, which is the actuator can be controlled by sliding mode control methods. Will the actuator be very sensitive to control chattering? Can Dr. Jin Chuan give give some indicating answers for this question?
Okay, so regarding the control chattering, so in our case here, we are using basically not using a smooth control algorithm here. We don't involve a lot of jumping of the control, which means that we didn't use any non-smooth control element in the controller. So we didn't see any significant chattering in the control. Okay. And regarding the sliding mode control, definitely this could be investigated in our dual stage. Actually, in our another paper that I didn't present it here, we indeed use a fast non-singular terminal sliding mode in the dual stage. Okay, and it improved the robustness as well.
Okay, thank you. And I have my own question. So have you considered the control saturation problem in your system?
Actually, this has been considered. Okay, so if you look at our system model in here, we actually have considered the saturation block here. And when you do the proof, when you do the proof of the stability, we also involve this saturation block in the proof already.
All right.
So that's why I say that that's one of the main challenge of dual stage. This has to be considered.
Yeah, definitely. Yeah, thank you. So now, because of limit time, so we only have one opportunity for raising questions. So if anyone has question, please feel free to ask. Because we have more external guests, so I believe they should have some questions. Yeah.
So this is my email address. So
Yes,
you could email me anytime. Okay, welcome to for discussion as well.
Yeah, of course. Yeah. Okay, so do anyone have questions? All right. Okay, so if we don't have any questions, so finally, I appreciate very much for Dr. Jing Chuan's, excellent talk for us. And during this, seminar, we learned a lot from the modeling to the control design, with the practical concerns. And finally, many thanks for Dr. Jing Chuan. And we look forward to see you in next month's seminar. Thank you.
Okay, thank you to all.
Thank you, Jing Chuan. Thank you. Yeah. Bye. Thank you.
Bye.